So to close the workshop, our final talk will be from Professor Arianna Menciassi from Scotland, Scottish in China. Her talk will be about artificial urinary system developed by soft robotic technologies.
So good morning to everybody, and I'd like to thank the organizer because they put together a fantastic program with many inspiring talk, both from the basic viewpoint and application. So let's go to another possible application of robotics that is related to robots that are inside the body. So the title is Artificial Urinary System Developed by Soft Robotic Technologies. And so I'd like to start from this slide. This is taken from a paper that we prepared some years ago together with some colleagues, Cecilia Lasky. She was one of the main actors in soft robotics, and Paolo Dario and Gianchetti. And at the time, we tried to make a sort of schematics where putting the different applications of soft robotics and how they are related to bioengineering. And we clustered the application also depending on the biomimicry level, that is on the y-axis, and the biocompatibility level, that is on the x-axis. And obviously, all the medical applications have an increasing level of biocompatibility from assisted device to surgical devices, to drug delivery devices based on soft robotics. While biomimicry is very high, for example, for body simulators, soft robotics is used very much for body simulators and for artificial organs. So we are focusing on artificial organs. And in this case, we are at the top corner because we need a high level of biomimicry because we have to fit the organ inside the body. So this is not just something nice to have, but it's a must. And also in terms of biocompatibility, explore the field of artificial organs by considering one of the systems that is closer to soft robotics, because also in our body, the urinary system is a sort of an hydraulic system. And we know that in soft robotics, we are using so much fluidic actuators, hydraulic actuators, and so on. I anticipate that I will focus more on the application. It is explained in this slide. So there are many people, 250, 500,000 new cases each year of persons with paraplegic problems or tetraplegic problems. In this case, they have the full anatomy, but they need some sensors to understand the fullness sensation of the bladder. And they lost also the detrusor contractility. The bladder is not a passive bed. There are some muscle called the detrusor, and these patients, they have no more detrusor contractility. Another case study that is even more relevant in a sense in terms of numbers deals with the cases of cancer, bladder cancer, or also prostate cancer. In all this cancer, in many of these cancer, you have to remove completely the bladder. And in this case, you have all the problem, not only the loss of fullness sensation, the loss of the treasure contractility, but you have lost completely the anatomical structure. So you have to rebuild the anatomical structure. Let's consider that at the moment, most people without the bladder, they have some channels from inside to outside directly from the kidney, and they have to collect the urine outside the body. So how to build an urinary bladder? So this is a sort of puzzle where you have to put together many different pieces. So there are many main pieces and some ancillary pieces that I will explain at the end of my presentation. The main pieces are the bladder, that is sort of a reservoir to put the urine coming from the kidney inside, the receptor for fullness sensation, and the treasure muscle for voiding the bladder, for squeezing. So let's see how we try to approach the problem of these three problems, these three pieces of the puzzle by using subaquatic technologies. Okay, the bladder is a bag. It should be a sort of bag without any elastic properties. Why? Because you cannot use a part balloon, let's say, because for the part balloon you can inflate, but you need pressure. While we need to have a bag that extends based on the dropping of the urine. So we, at the beginning, we used a soft system, but that was, let's say, hybrid, soft rigid, based on polypropylene and acetate. We fabricated a multi-segment sealing structure, and we used a thermosealing for the self-foldable structure. This was not very large in terms of volume, but being self-foldable, it was able to expand without any additional force. And the fact to have the two faces flat, it's also helping if you want to put some coating, for example, some urine-resistant coating on the internal faces. So we were quite happy with this shape because for a set of reasons, it was working quite well. But medical doctor for the implantation, they were not so happy because they complained that it is a little bit rigid and so not fitting very well inside the body. And so together with them, we prepared a different, more soft design. That is, there's a silicone origami-based structure obtained by injection molding. Again, this is self-foldable, but more flexible, as you can see in the movie, to be implanted. The three channels that you see, two channels are for the kidney connection, and the last one is for the urethra, so for the output, let's say. We used in this prototype Moldstar and EcoFlex silicone at the beginning, but after this we did some simulation to understand which is, in addition to the overall concept, which is the best combination of material and the best combination of thickness, because we had to select the thickness for the wall, the thickness for the foldable area, and which is the best material also in terms of fatigue behavior. So at the end of our simulation, we selected Moldstar 15 with a thickness 2:1, 2 for the wall, 1 for the area that you have to fold. We also faced the problem of the internal pressure. Why? Because it's very important from the physiological viewpoint that during the volume increasing of the bladder, you don't become a certain intra-bladder pressure that is the physiological one. That is the red line in the picture. And so for understanding which is the pressure, we did both simulation and experimental bench test analysis based on simulating the effect of other organs around our bladder, because our bladder is not alone in the abdomen, there are many organs around. So we did this both in console and also simulating additional organs by using water party balloon with water inside. And we set everything in order to be sure to be, even against obstacles that are other organs, to be under the level of the physiological intravesical pressure. Okay, so we have seen the first part of the story. Let's see the second the second piece of the puzzle, receptor for fullness sensation. Obviously, having different shape of the bladder, you need a different solution for the sensing. So for the first bladder, that was the parallel phase bladder, we used magnetic sensor. Why? Because the final objective is to measure the volume of urine inside the bladder. But let's say that we have this foldable structure that open like that. So by estimating the distance between the two phases, you can have a measurement of the distance and then the volume. So we integrated more than one, 4 or 5 magnetic sensor or effect sensor in order to have also some redundancy and to have the same measurement or approximately the same measurement also with a change in geometrical fluctuation, because you can have the same volume of liquid but with a different shape of your bag because you are not alone in the abdomen, so there are other organs. So we obtained a precision of about 12-15% in the estimation of the volume. And we were quite happy also in terms of implantability. We did several tests on human cadavers, and the overall sealing of the system and the operational test done on cadaver was quite successful. But as I mentioned, this was not the best shaped for medical doctors. This is good for implantation in a cadaver because you can open quite well all the abdomen, but not for a real patient when you have to reduce the incision and to have a minimal invasive approach as much as possible. So how to make a sensorization of our final bladder, that is the origami silicone bladder. So, and how to match the sensorization, flexible sensor, the sensorization with something flexible that is compatible with our silicone structure. So we use a resistive textile sensor, put on the fold, again in a redundancy configuration, put on the fold, onto the fold of our bladder, and estimating the opening of the fold. So maybe you know that resistive textile sensor and textile sensor in general, they are not very good in terms of linearity. We had to put the working point of the sensor in an area where the sensor was quite linear. And we integrated everything onto our bladder. So then we did some calibration. What you can see in this movie are the calibration in terms of volume and 3D shape reconstruction. So basically you take the bladder, you inject water, and you monitor the signal from the different sensor. And from this monitoring, you try to derive the volume inside the bladder. So in consideration of all the flexibility of the bladder, we had an error that was between 10 and 20%. And we were not so happy about this result, but this is one case, as mentioned before by the previous speaker, maybe this is not very precise, but this is very volumetric, because if I ask you now to estimate which is the volume of your bladder, you cannot give an estimation, but you have enough sensation to understand if you have to go to the toilet or not. So 20%, especially when you have a limited volume inside, it's more than enough, because it's more important to have precision when you are at a high level of volume collection. Okay, this system was much better in terms of implantability, so you don't need a large access area because you can fit quite well. And in the abdomen, medical doctors were also able to connect the different channels, or different anatomical channels of the body. And during the implantation and just after the implantation, we did some fluoroscopic images for monitoring if the filling of the bladder was correct, if there was any reflux, and so on. Okay, so now let's go to the last part of the last main block of the puzzle, the detrusor muscle for voiding. Let's say this is the most traditional sort of robotic activities, because being this system a fluidic system, we decided to put fluidic actuators around our bladders to help the squeezing. So for the very first design of the bladder, we used the fluidic actuators in bellows configuration or in origami configuration, put on the top or in the lateral side of our bladder. And so by inflating with the injection of liquid, by inflating the actuators in the first case, you have the squeezing of the bladder, and in the second case, by putting the water out, by reducing the level of the water inside the origami actuator, we squeeze the bladder. We did some evaluation of the efficiency of the voiding without any additional valve. So we compare in the red square, we compare the bladder without any actuation in a flat configuration. In this case, you cannot void the bladder, so you just go half of the liquid inside. While by putting the different actuators, origami and bellow, we reach the voiding efficiency close to 90%. For the final bladder, that was the silicone based, we used other balloon actuators based on simple stiffer and softer layer of silicone that you can inflate to squeeze the bladder. And in this case, we reached again a very large level of voiding efficiency, close to 100%, 98.9%. And another solution that we tested, I have to say that it was a little bit less promising in terms of integration of the bladder, but it was not so bad, in my opinion. By improving the manufacturing and the sizing of the different components, it can be better. This was a, let's say, traditional water bomb design, where basically you have two layers with foldable structure inside, and by keeping out the water or pulling in the water, you can have this very evident shrinkage or dilatation. Okay, and I told you that these are the three main pieces of our urinary system, but let's say that there are also some very relevant ancillary components. For example, the ureteral valves to avoid the backflow of the urine to the kidney. Originally, the very first ureteral valves were completely passive. We used just two foils to be put inside the bladder, and when you have the urine pressing the two valves, you cannot escape, let's say. This was very effective for the first bladder, the one fabricated in polypropylene and acetate, but this was not so effective with a different geometry, because if you have to fit something like that in circular channel, this is not so effective. And in fact, with this silicone bladder, when we implanted in the peak, we observed that there was a reflux behind. So now we have developed some valve, still without any electronics, but more adequate to be operated inside the channel. One has this butterfly shape, another one is a simple cap valve. And we have both modeled the fluid interaction, and we have tested in vitro. And as you can see from the graph, obviously, by using the valve, you have a slower filling of the blood, but at the same time, you never overcome the physiological pressure that you have set, because at a certain point, the valve are doing their job, so they close. Another component is the sphincter, the urethral sphincter, to guarantee continence during filling, because otherwise you fill in the bladder, but you cannot keep the urine inside. Also in this case, in order to be coherent with all the sub-robotics design, and also to exploit the reservoir, because inside the body you need a reservoir of water, sharing the water between the detrusor and the sphincter. We are developing this soft valve, fabricated again in silicone, with input-output and the control input. So depending on the control input, you can close or open the valve, and you should manage the reservoir liquid in order to manage the detrusor and the sphincter. And finally, there is one important part of the overall system, that is the electrofluidic circuit for the activation of the hydraulic actuators. We are still under the development of this electrofluidic circuit. We presented the first design during the last robotics conference in Lausanne. So basically the idea, we needed to fit everything inside the body. So the idea is to limit as much as possible the number of valves and the number of pumps. So with the optimized the fluidic pathway design, we are able to manage the sphincter, that is a sort of outlet for the water distribution, and the detrusor, that is another outlet, by using just 3 valves and 1 pump in a system that is quite miniaturized. So the movie should illustrate the blue balloon is the reservoir, and the 2 yellow balloons are 2 outlets. One can go to the detrusor of the bladder, one can go to the sphincters. Okay, so I want to close my presentation with some reflection about all the story. So we have used this self-design strategy for the entire system, for the entire urinary system, because I started my presentation saying that the urinary system basically is an hydraulic system. And we fell in love with the self-design, but the winning solution for just some components, some system components, can be different. And I want to tell you a very briefly story, because before this project, we were asked to develop not the full urinary system, but just the sphincter. Just a sphincter for people, especially after prostatectomy. So they have the bladder, they have everything, but they needed the sphincter. In this case, we designed a system totally rigid. So it was based on the main requirement was you have to use the sphincter without any major surgical operation, but by using just the entry point of the urethra. And so we designed this cylinder with a magnet inside, a sort of a soft precursor, and the polymeric valve. So when the suffix cursor was up, thanks to the spring, the valve was closed. When you approach from outside the magnet, you translate the red cylinder, let's say, so you disengage the valve and you can open the valve so you can urinate. This is no electronics inside, just some magnets, and very, very, very simple to be, or at least in principle, very simple to be implanted. So in this movie, you just can see the operation of the system. At the end of the story, we used a stable solution for the cursor in order to change to avoid to keep the magnet all the time during the urination. So this system was tested first of all in a cadaver to see if it was really easy to be implanted, and it was implanted in less than 5 minutes. And so we developed the final system. You can see here all the different pieces of the final system. We did the validation in patient for 28 days after prostatectomy. And so after the first validation in patient, now there is a company. I'm not involved in the company, so I have nothing to disclosure, but just to say that it was a winning solution based on soft robotics. So Vicky opened your introduction with this graph coming from a sense robotics paper of Mike Tolley, and trying to follow in the story of soft robotics from the first publication to institutional funding, startup, Robosoft company, Robosoft conference, and now there is the question. We are now in a position where we just wait for a decrease of interest and minimal impact, or we have the possibility to try in the field and to obtain high input. So what is missing to take the winning branch? So I have no answer, but this is my personal lesson learned. So we have to identify the most promising, impactful application where the soft robotics design can add value. So robotics cannot be employed as a holistic solution for all the problems. So in a sense, it's a powerful design strategy, more a relevant tool that you cannot miss in any medical design workshop. So I'd like to thank you very much for your attention and all the team for helping me in developing this technology. Thank you so much.
Thank you very much for the great talk and the picture. And any questions for Professor Menciassi's talk? Yeah, please. Sorry.
So very quick question. So are you using the kind of soft actuator to control the urinary bladder? So how can you control the pressure? Because the urinary bladder is quite sensitive for the pressures. I'm just curious about it.
So it's a very good question. So in our application where the bladder is artificial bladder, we don't need to control the pressure, just squeeze, because there are no sensors. But your question is very relevant because, for example, for paraplegic patients, they have their bladder. And for example, some actuators, the water bomb actuator originally has been developed for paraplegic persons. So to put the actuator around the bladder and to squeeze. And in this case, you have to take care not about the sensor, because you have no more the sensing ability, but you have to take care of the tissue. Because at the end of the story, the problem is that the tissue of the bladder has been designed by nature to contain urine. So if you can use the existing tissue, for example, in paraplegic people, you can use the existing tissue, this is much better because you avoid any problem of infiltration, bacteria, and so on.
Thank you.
Time for the last question. Yeah, please.
Hello, Professor. I want to I'm the postdoc from Duke NUS Medical School. So actually, I'm an engineer in medical school.
Okay.
So I want to ask because I have a very strong agreement on your opinion on the precision control of the bladder. Yes, because I feel it's quite difficult to balance between the practical meaning and the scientific part. Yes, because sometimes the doctor, I mean the clinical doctors, they may prefer more practical but more simple way to do that. But if we want to build up some scientific impact, we will try to seek more complicated way to build that. So, but I saw your work actually balanced quite good on the practical and the scientific way. So may I ask you for some advice on how to do this?
So I think I can provide just my humble advice. It's very important. So you have mentioned that you are a medical doctor but working with engineers. So or something like that. Okay.
I am an engineer
working with medical doctors. Okay, so this is the key. This very tight collaboration is the key for the success, because in some cases the priorities of problems can be different and we have different vision. So for example, in this case, we were very worried about the precision of the estimation of the volume, while we were very happy with the previous system with the Hall effect sensor, because in that case the precision was much better. But at the end of the story, the medical doctors changed the priorities for us, and it was good. So the only possibility is trying to work together and to share languages and to share experience. So my only suggestion is to promote as much as possible this collaboration between people developing technologies and people having application, but not only in the medical field, but I think also in industrial application or in sea exploration and so on.
Thank you.
Okay, thanks, Dr. Menciassi, for talk and the answers. So due to the time limitation, maybe we have to skip the panel discussion, and that's all for our second soft frontier workshop. And hope that we can see you. Sorry, wait a minute. In this workshop, we have talked about practical applications in soft robotics, about industry, deep sea, and surgery. And I hope that we can see you in the third and fourth soft frontier workshop in the future. Thank you much for coming, and see you again in the future.